In this video, I'm going to talk about different example about evaluating the derivative of a function at a point f prime a, right? If the fx is involving, if the function is involving a piecewise function, so can we directly apply the formula, right? The meanings of that, we're applying this formula here. The first principle at a point. So means that the limits as x approaching a for fx minus fa divided by x minus a. This formula here. So it means that we're going to apply this one. But actually, if there is a piecewise function, you know, piecewise function, they have different function at different domain of x. So then we have to know that, understand the concept of limits here, right? Because this is a piecewise function, right? So in order for this derivative to exist, in order for the f prime a to exist, f prime a exists, means that if there is a piecewise function, there probably kemungkinan the f prime a does not exist here, because we need to consider when there is a piecewise function, when fx is a piecewise function, a modulus functions, right? Because modulus function can be rewrite as a piecewise function. So generally, if there is a piecewise function, a type of function that is named as piecewise function, then we have to consider limits from both sides. We have to consider the limits from the right hand side for this function. So the fx minus fa over x minus a. So then you have a value of L, for example, you have evaluate, and your limits, the limits from the left, can you see from the right and from the left? So for the functions, why we have to evaluate both? Because they have different function when more than a, when less than a, right? So then let's say you are getting another value, a value m. So what happened? Okay, the concept here very important here. What happened when L is not equals to m, right? Means that the value of L is not equals to m, right? So this shows that f prime a does not exist. So okay, you have to understand this. So if L is not equals to m, means that the f prime a does not exist. The value of it does not exist. So this is also, we also can say that, okay, this is the first statement here, f prime a does not exist. Or we can say that the function fx is not differentiable, able to differentiate, differentiable at point x equals to a. These both have the same meaning here. F prime a does not exist is the same as fx is not differentiable, cannot be differentiated at this particular point here. So these two statements support that if this provided that the limits of the right of the function and this function, the gradient function, is not same. It's not the same. So what if this is the first concept here. So secondly, what if the L equals to m, right? L equals to m. We said that f prime a exists. F prime a exists. Why exists, right? Because the right and the left are the same. The value are the same. Means that the limit as x approaching a will exist, right? Exist. Or we can say that fx is differentiable. This is not differentiable. This is differentiable. Keboleh bezaan. Differentiable at point x equals to a. This is a very important concept here. So means that if this is differentiable, these two values will be the same. These two, limit from the right and from the left, is equal. Alright? When these two are not the same, L is not the same as m, the value, then we said that the f prime a does not exist, or we said fx is not differentiable at that point here. So this is the concept. So please jot down this concept before I solving a function for you. I want to show you, after this concept here, I want to show you how to evaluate a piecewise function. Alright, this is what I mean for a piecewise function. Okay, you have piecewise function. So when less than 1, there is a value, there is a function. More than 1, there is a function. So in this question, we want to know whether we want to evaluate. We want to evaluate f prime 1, right? We evaluate the boundary, you know, the derivative of a function. The derivative at a point. The point now is the boundary value here. So we don't know, because we don't know which function we should choose, right? So when less than 1, this is a function. When more than 1, this is a function, right? It's not a single function. There are two functions. So it's defined according to their own domain. So now how to evaluate the f prime 1 here, right? So then of course we have to apply the formula for derivative at a point. So you know that the f prime 1, f prime a is defined to be the limits as x approaching a of fx minus with fa divided by x minus a. In these cases here, so we know that the a is 1. So limits as x approaching 1 of fx minus f1 divided by x minus 1, right? So this is the one that we want to evaluate. But usually we will directly evaluate. But because of this is a piecewise function, remember it's a piecewise function, so we have to consider the right and the left limits here. The meaning here will be, I will consider, because this is a piecewise function, okay, I repeat many times, it's a piecewise. So we have to consider limits as x approaching 1 from the right, right? You know that x approaching 1, so we want to approaching from the right and from the left. So now we have from the left fx minus with f1, it's the same, f1 x minus 1, right? For the same function, for fx minus f1 over x minus 1, just this one we write as x approaching 1 from the right. So, okay, now we evaluate this one. So let's see what happened. So, okay, you know that the limits as x approaching from the right. From the right means something greater than 1, right? So we have to choose the function. This is the one that important here. So we have to choose the function which is greater. This is less than 1. This is from the right. Right? Approaching 1 from the right. So 1 plus, so greater than 1. So we should x square, right? You are choosing the function to be x square. F1 is x equals to 1. So you substitute to the function, not this, but this one, because there is an equals here, equal sign here. So you're putting 1 here, right? You're putting 1 here, you will have, means that your F1, you can evaluate first before you put in. F1 will be 2 multiply 1 minus 1, which is 1, right? So then you have F1 to be 1 over with x minus 1 here. Alright? So now you can evaluate the limits. As you know that you see these cases here, you put in the 1, you have 1 minus 1 square minus over 1 minus 1. It's a case of 0 over 0, undefined, right? So the most proper way is you're doing factorization. X plus 1 over with x minus 1, right? X minus 1. Then you eliminate the common factor here. So later you can putting the value 1 plus 1 is 2. So means that from here, okay, I jot down my answer here, means that the limits of x approaching from the right for this function is equals to 2, right? So now we're going to evaluate the limits of the this function from the left. Okay, from the left, so of 1, so which is fx minus f1 over x minus 1. 1 from the right, 1 from the left. So okay, let's see. Alright, now we consider the limits of x approaching 1 from the left, right? Just now you're finding that from the right you're getting 2, so now you just need to know from the left. So from the left here, so what is the function? Okay, fx minus with f1 over x minus 1. So what is the chosen function? So less than 1. So less than 1. So I'm choosing 2x minus 1 here, right? Minus with f1. f1 you have found, which is 1, right? Which is 1 over with x minus 1. So we have to evaluate this limit here. 1 from the left. So you have 2x negative 2 divided by x minus 1. This is also a case where you put in 1, you're getting 0 over 0, right? So we can factorize the common factor here. So the limits x approaching 1, so will be 2x minus 1 over with x minus 1. As you factorize the 2, right? So the x minus you can cancel out. Limits of a constant, you will still get back a constant. It's also 2, right? So the right is 2, the left also 2. Means that the limits for x approaching 1 exist here. So you see, if you see that from the right, from the right is 2, from the left of this function also 2, and this function from the right is 2, from the left also 2. So means that x approaching 1, the limits exist, which is giving the value of 2. Means that f prime 1 is 2. So it's differentiable. Alright, it's differentiable here. So we can say that f prime 1 exists. So which is the value of 2. Right? So this is how we evaluate derivative at a point, the value at a point for a piecewise function here. So, okay, I have not yet end the video yet because I want to show you what is the meaning of differentiable here. What is the meaning of differentiable here? So, for this question, right, we go deeper, right? As we learn maths, I like to go deeper to every knowledge that I have here, so that I really learn maths. Okay, so you see. Okay, what is the meaning here? That you said that f prime 1 is 2. Okay, this is 2. So, okay, what is the meanings of f prime 1 exists in the geometrical representation? All right. So I'm going to sketch the graph for you. All right. So I'm going to sketch the graph for you, and you just look at what is happening at that point. All right. I have already drawn for you. So you see that 2x minus 1. So this is a graph before 1. So this is a graph for 2x minus 1. And after 1, this is a quadratic, x squared. So if you sketch the graph fully, so you can see this is a quadratic, right? This is a quadratic. So, so this is a straight line. So you see that what is the meaning of f prime 1 exists, right? So let's look at the diagram here. So what is the meaning of f prime 1 exists? F prime 1 exists. F prime 1 exists means that there is a gradient which is 2. It means that here is a smooth transition here. The smooth transitions of the values. So it means that if you have a roller coaster with this shape, if you're passing through the roller coaster, passing through this point, the roller coaster will going through. Because at this particular point, the transition is smooth. Means that from linear become quadratic, it's like never happened in anything. It's like very smooth. It's like linear to become a quadratic. It's a very smooth transition. If you look carefully, this is a smooth transition from linear become quadratic. So it's a smooth transition. Means this line is very smooth. That's why they have f prime 1 exists. So what happened if you have a graph with this way? So means that you have sharpened. For example, you have sharpened. This is called sharp point. As you see that this one is smooth, right? It's smooth transition. This is not smooth transition because you see from linear, yeah, there may be a quadratic, some quadratic, here may be a sharp point here, right? This one is with the one that the f prime a does not exist. Does not exist. All right, does not exist. Means there are no gradient for a sharp point. So means that differentiable Okay, now I'm going to tell you that the meanings of f prime 1 axis is also can say that fx is differentiable at x equals to 1. fx is differentiable at x equals to 1. The meaning here is in physics or in physical phenomena, this type of transition we say smooth transition, where the graph very smooth. Alright, there are no sharp point. Means that we can, using mathematics, this concept of their first principle, to identify the sharp point. So whether that the one turn to this function, is there a sharp point at that point? No. Based on the calculation here, you have proved that the limit exists. So means that there is a smooth transition. So this is for your extra knowledge. Alright, hope you look at it. So I will go for another 2 video about differentiability.